Okay, this is part 2 of section 2.6, Infinite Limits at Infinity. This is from the James Stewart Calculus Early Transcendentals book, and we're going to go over some examples of taking limits as x goes to infinity of a function and what it means for us to have infinite limits. Okay, hopefully from a pre-calculus book, you have reviewed or are familiar with your standard power function, and your standard power function looks like f of x equal x to the n, where n is bigger than 0 and n is a natural number. And what's a natural number? A positive whole number. So we don't have any radicals in there. They're just positive whole numbers, and we don't have rational expressions, 1 over x to the n. Remember, when n is even, we tend to have functions that look like the U-shaped or the parabolic shape, and as x gets larger and larger, or as the exponent on x gets larger and larger, our U-shape becomes steeper and steeper, because you can imagine 5 million squared for x squared. If I plugged in x equal to 5 million on x squared, I'd get a really large number. But if I plugged in 5 million on x to the 6th, it'd be even larger. Just imagine how many zeros you have there. So of course it's going to go to infinity that much faster. Good. Also, if n is odd, we end up having this snake shape, or this kind of S curve. And you can see that as x goes to positive infinity, our function outputs are headed towards positive infinity on x to the n. And if x is approaching negative infinity, our outputs on x to the n are approaching negative infinity. So that's good to note for power functions, and it kind of helps us when we go to calculate limits at infinity. Okay, so what does it mean to be an infinite limit? That means your limit is equal to infinity or equal to negative infinity. Infinite limit at infinity means x is going to infinity. Okay. In general, if x is approaching a particular number, the general strategy is, if I get a 0 over 0, I want to factor out the x minus a, because that value of a is a 0 of the top and of the bottom, so I can factor a common factor from the top and bottom and continue to find my limit. With limits at infinity, the strategy is to factor out the highest power of x from the top and bottom, cancel out equal magnitudes of infinity, and use the idea of, just recall, if we end up with the limit as x approaches infinity of x to the n, if we end up with x's in the numerator, we're going to infinity, right? If the limit as x approaches infinity of 1 over x to the n, we're going to 0, okay? So we can still use that idea. And also, if we are going to the limit as x approaches a from a one-sided, or even from the left, because in the case of limit as x approaches infinity, it is a right-handed limit, or it's coming from the left-hand side, sorry. That's a left limit. So if the limit as x approaches a from the left of an f of x is going to go to 1 over 0, that's going to be a plus or minus infinity. Good. Sometimes that two-sided limit would not exist, but remember, plus and minus infinity don't exist either. But if you ever get a 1 over 0, look to either say do not exist if it goes to two separate infinities, or it could be plus or minus infinity. But going to infinity, positive infinity, that's a left-handed limit, so it's a one-sided limit, so you're just going to get positive or negative infinity there. If you're going to negative infinity, That's a right-handed limit. It's a one-sided limit. So if you get 1 over 0 when you go to calculate values, then you would end up with positive or negative infinity. And you'll see that in example B down below. All right, so if we're taking limits at infinity, you can use the strategy of factoring out the highest power. And I see the highest power is x to the 5th. So I can say that this is the limit as x approaches minus infinity of x to the 5th. And this is going to be minus 3 plus 4 over x cubed minus 1 over x to the 4th plus 17 over x to the 5th. I can now use my strategy and my rule sets. The limit of a product is the product of the limits. The limit of a sum is the sum of the limits, limit of a difference, and whatnot. So x to the 5th, knowing my power functions, and I'm going to minus infinity, this is going to minus infinity. And you can think of minus infinity to the 5th power. Infinity times infinity 5 times is going to be infinity, but minus 1 to the 5th is negative, so we're going to negative infinity. Negative 3 is going to minus 3. Going to infinity, that's going to 4 over infinity, and from the part 1, we know that this is going to 0. Minus 1 over x to the 4th, that's going to 0. 1 divided by a bigger and bigger and bigger number is getting smaller and smaller and smaller. And we have 17 over infinity, and that is also going to 0. And we can say that this is going to minus infinity times minus 3. And a negative times a negative is a positive, and 3 times infinity is infinity. So we can say this is positive infinity. All right. Looking at the next one, we can factor out our highest power, and our highest power is x to the 3rd. So this is going to equal limit as x approaches infinity of x to the 3rd power times 9 plus 5 over x to the 3rd power over x to the 3rd power 1 over x plus 1 over x cubed. I want to cancel equal magnitudes of infinity, and I'm going to use my limit laws. The 9 limit of a constant is the constant. This 5 over x cubed is going to 5 over infinity, and 5 over infinity is going to 0. 1 divided by infinity is going to 0. 1 over infinity cubed is going to 1 over infinity, which is also 0. So this is going to 9 plus 0 over 0 plus 0. That's going to 9 over 0, and it's from the left, right? Because we're going to pop x going to infinity from the left. So we know this is going to infinity because that is a positive over a positive. All right, this one, remember that some of our indeterminate forms, we cannot have infinity minus infinity. We can't have infinity times 0. And we can't have 0 over 0. And we can't have infinity over infinity. We must algebraically manipulate. Just like we did in the first example. So, if we have to algebraically manipulate, notice here that if I were to plug in infinity, this is going to infinity squared plus 2 times infinity minus infinity, and that's going to infinity minus infinity, so we have to manipulate. Whenever you have a radical minus or plus in an expression and you need to manipulate, consider multiplying on top and bottom by the conjugate. And what's the conjugate? The opposite. You want to consider a squared minus b squared equal to a minus b times a plus b, right? And so that's why we have those conjugates are the plus or the minus, the opposite. So I'm going to start with the limit as x goes to infinity of the square root of x squared plus 2x minus x. And I'm going to, since I have the a minus b part, I'm going to multiply by the a plus b part. And so I'm going to multiply by x squared plus 2x plus x. And if I multiply by that, I must divide by that because I can only multiply by 1 without changing the value of the limit. Because remember, the limit of a constant times a function is the constant times the limit of a function. And if I just multiply by any random number, it's going to change the value of the limit, and I want my limit. So I know that this is going to equal a squared minus b squared, right? So this is going to equal the limit as x goes to infinity of the square root of x squared plus 2x squared minus x squared, right? Because that's my a squared minus b squared. And in the denominator, I have 1 times that radical expression, and that is x squared plus 2x plus x. So now I'm going to clean things up. I'm still algebraically manipulating. So this is going to be the limit as x goes to infinity, and the square root squared is going to be what's underneath the radical. And we have x squared, so that's going to be minus x squared. And we have x squared plus 2x plus x. I can clean up what I have in the numerator, and I get x squared minus x squared. So this gives me the limit as x approaches infinity, and I'm going to just write it out here as the simplified version. Now, technically, the highest power in the entire expression is 1 because the square root of x squared is x. So if I'm going to factor out an x, so because we're still taking a limit as x goes to infinity, and the strategy is to factor out the highest power of x. So in doing that, I see that the highest power is x because x squared square root is still x. So I'm going to say that this is going to equal x times 2 over, and I'll do baby steps. If I'm going to factor out an x squared, that's going to be 1 plus 2 over x, and I still have plus x. That's going to give me, now I can take the x squared and take it outside, and that's going to give me my x. And now I can factor out my x from the denominator. And that will give me the square root of 1 plus 2 over x plus 1. I can cancel my common factors. And now I can start taking my limits. So this is going to go to 2 over the square root of 1 plus 2 over x is going to go to 0, or 2 over infinity. And then I have plus 1, and that's going to go to 2 over root 1 plus 1 is going to be 2. And my answer here is going to be 1. That's what my limit is. Good. All right. Moving right along, the limits at infinity of exponential and logarithmic functions rely on the knowledge of their perspective graphs. So don't forget that if I have e to the x my e to the x when x is bigger than 1 looks like that, and when x is negative, it will actually flip across. Or fractional. E to the x. Okay, or when e to the x are bigger than 0, sorry. And this is e to the minus x here, right? Because we do a horizontal flip. And remember that your natural log looks like this. Good. And this is my e to the x, and that's e to the minus x. So we can see with this one, as x goes to infinity, my function outputs are going to infinity. And as x goes to negative infinity, this is x approaching negative infinity, we are headed towards 0. Good, because it's going to e to the minus infinity, and that would be 1 over e to the infinity, and 1 over e to the infinity is going to 0. And we also see as x approaches 0 from the right, our function outputs are headed towards minus infinity. And as x goes to positive infinity, our function outputs are headed to infinity. So those are good to keep in mind when calculating your limits. All right. So how do we do these? Okay, so we have, we can say that I can rewrite this as limit as t goes to infinity of 5 times 1 over e to the 0.02t minus 1. And if I plug in infinity, 0.02 times infinity is going to be infinity. So this is going to go to 5 over 1 to the e times 0.02 times infinity minus 1. The limit of a constant is a constant. And this is going to 5 times 1 over e to the infinity minus 1. That's going to 5 times 1 over infinity using those rules up top. And 1 divided by infinity is giving me 0. And that's going to give me minus 1. This is as x approaches pi over 2 from the left. So I just want to review that secant theta, or secant x, is equal to 1 over cosine x. Good. And if you remember your cosine function is going to look like this. That's cosine x, and this is pi over 2. Good. So if we're coming from the left, we see that our function outputs are positive cosine approaching 0, right? Cosine is approaching 0 there, so just to take a look at that secant in there. So I can rewrite this as the limit as x approaches pi over 2 from the left of e to the 1 over cosine x. And I can see that this is going to e to the 1 over 0, right? But 0 in a positive way, right? So this is going to be a 1 over 0, but it's positive, so that's going to e to the infinity. We never really achieve the 1 over 0 because it would be a vertical asymptote for secant, but we get really close to it, and when we get really close to it, we're getting there from positive values, so we would have a positive infinity. 1 divided by a smaller and smaller number is getting bigger and bigger, but it's still a positive number, and e to the infinity is going to infinity.